the data table and you were given a table like this. Okay. I remember I taught you also how to derive half-life. I wanted to quickly show me the derivation. Derivation of half-life for a second order reaction. For a second order reaction. Derivation for the half-life of a second order reaction. How will it be? Now remember that the integrated rate law of the second order reaction is what we have 1/2 E equals to KT plus 1/E0. I don't know if you remember this. Now using this now, I want to derive the half-life for a second order reaction because this is the integrated rate law for a second order reaction. I want you to derive the half-life for this reaction. Once you get your answer, just post it, just write it here so I can see. Write it there. Well, to do this now, we say that for half-life, which I'll call CR, we know that our final concentration, E0, should be equal to 1/2 the initial concentration, which is E0. Are you getting me now? We know that for our half-life, the final concentration should be equal to half of the initial concentration. That's half-life because it is the time taken for half the concentration of that reactant to get used up. You get. So we are going to be effecting this into this equation here, and that will enable us to get our half-life for a second order reaction. So what are we going to be doing? We are going to be substituting A0/2 in this expression right here, and that will be what? Substituting this into this, you'll be having 1/A0/2 is equals to KT plus 1/A0. Of course, the implication of this here is going to be that we'll be having 2/A0 equals to KT plus 1/A0. I remember that this T is no longer T because we have done that this is now half-life. So you are going to carry this to this side and you'll be having 2/A0 minus 1/A0 is equals to KCR. I don't understand. Is it our network or what? What's wrong with the network of most of you? It's really very bad. Okay, then we now have what here? We know that this A0. In order to do this, we just look for the LCM. And we know that the LCM will be A0. So A0 divided by A0 is 1. 1 times 2, 2. A0 divided by A0 is 1. 1 times 1, 1. Which is equals to KCR. So we can say from here that 1/A0 is equals to KCR. So divide both by K to obtain the half-life of the second order reaction. I get what I'm saying now. And that will mean our K cancel K, C/half is equals to this expression here will give you 1/A0. So that's it. That's the half-life a what? For a second order reaction. So it's actually very easy. It's actually very easy. So I want us to attempt to obtain the half-life for a zero order reaction. Obtain the half-life for a zero order reaction. Just try it by yourself. All you just have to do is from the general zero order reaction, for zero order now. If you're doing for zero order, if you're obtaining for zero order, we remember that what? We just remember that our equation is what? It's going to be A into minus KT plus A naught. That's our expression for a zero order reaction. That's our expression for a zero order reaction. So using this now, I want you guys to attempt it. Obtain the half-life for a zero order reaction. The equation for the half-life for a zero order reaction. Just attempt it quickly. Once you get it, just write your answer down. Has anybody gotten the answer? I don't know, my laptop is really giving me problem. I'm trying to set it up so I can get questions. Nobody has been able to get the answer right? I told you to obtain that kind of half-life now. You just tell yourself, because these questions come out a lot in the past question. You check your past question, you see where they say derive the half-life for a second order reaction, derive the half-life for a zero order reaction or a first order reaction, stuff like that. So for a zero order reaction, the half-life will become what? You say, let A, that's your final concentration. Since you're talking about half-life, it will be equal to half of your initial concentration, which is A naught. Okay, so only wrote the answer there. Minus KT plus A naught. That's not the half-life, that's just the expression. I want to get the half-life from the expression. So look at it. You will now say that this is what you're going to be substituting in this place for your A. So we will now be saying that A naught, instead of writing A, that is A naught over 2 is equal to minus KT plus A naught. Are we following now? Then before that, we can now say that what? And that's collect like terms. This A naught plus A naught comes to this side, it becomes minus A naught. Or rather, we can just carry this minus KT to this place, like I'm posting the take this one there. Now giving us KT half equals to A naught minus A naught over 2. Are you seeing this now? Then we can now go further to see that our KT half is equal to what? By the time you subtract these two things, you have 2 here, 2 divided by 1, 2, then we have 2 A naught minus A naught. And having KT half is equal to what? A naught over what? Over 2. Divide both sides by K. So we'll be having T half, that is half-life of a zero-order reaction, is going to be equal to what? To A naught over 2K. Now, these are important techniques that you must have in your mind. So you can write it down. You can write it down. And write it down. Please, if you are done writing it down, just inform me so that I can wipe off the board. If you are done writing it down, inform me so that I can wipe off the board, please. Are we done? Please, if you can also take screenshots so that we can be faster. Instead of writing it down. Can I wipe it off? I think I'll wipe it off now, please. So you can take screenshots right now because I want to clean. Okay. Okay, now we'll talk about reaction mechanisms. Before we start solving questions from the integral rate law, half-life, and stuff like that, we have talked about from experimental data. Now, I told you guys if you need more questions, you can come and meet me. We solved questions on the previous video on experimental data. Now, I want to look at the reaction mechanism. Now, what do we mean by reaction mechanisms? These are the series of steps that occurs before a reaction or a complete reaction can take place. That's what we refer to as reaction mechanism. The series of steps that occurs before a reaction can take place. Now, what you must know is that in chemistry, when you write any reaction and you balance all those reactions, the reaction actually doesn't just happen the way you wrote it. It doesn't just happen the way you wrote it. There are series of steps. There are series of steps that must have occurred. There are series of steps that must have occurred for the reaction to take place. And now the series of steps that occurs before a reaction can take place is what we call the reaction mechanism. I get me now. And those series of steps, we call them elementary steps. We call them elementary steps. So whenever you hear the word elementary steps, I get me now. Those are the little steps that occurs before a complete reaction can take place. So please, you have to write it down. Reaction mechanism. Reaction mechanism refers to the series of steps, that occurs before a reaction is completed. These steps are referred to as elementary steps. So these steps are what we call elementary steps. And I think I've made this note to you guys that it is very, very possible for you to obtain your order of reaction from an elementary step. You can obtain the order of a chemical reaction from its elementary step. We've done for experimental data already. So from elementary steps, you can also obtain your distance. Now, in a reaction mechanism, there's some things you need to take note of. You have to be able to look out for the catalyst. It is important in a reaction mechanism to obtain the following. Now, in your reaction mechanism, you must know that there are three things that you'll be able to obtain. The first thing you'll be able to obtain in your reaction mechanism is your rate law. Which I should remind you is written in this format. R equals to K reactants raised to the power of their order. So you can obtain your rate law. Another thing you can obtain in a reaction mechanism is you can obtain you can know your catalyst. You can find out your catalyst, and you can also find out your intermediary. And these are the three things you must look out for: your rate law, your catalyst, and your intermediate reagents. Are you getting me now? Now, your rate law, because you can ask you to obtain your rate law from your reaction mechanism, you make use of the slow elementary steps. We still look at these things critically in technical ways, like through reactions. So you have to obtain your rate law from the slowest elementary step. You get what I'm saying now? You see, they'll give you 2 or 3 elementary steps or 4, and then after doing a lot of casting now, which we'll be doing now, to write out your rate law of the overall reaction, you need your orders, your rate order, and that can only be obtained from the what? From the slowest elementary steps. And remember, I said something. I said that to write your rate law, you have to be dependent. Those rate law expressions are only dependent on the reactant. They are not dependent on the product at all. You understand? So, what is now a catalyst? Or let's just write it there. The slow elementary step is the what? Is the rate determining step. For example, now look at something. If I say that I and Tolu now should run together, and they say that if we must get to, like, we have to run from here where I am now to Unilag, and they say that if we must get to inlet, we must get there together. Who is going to determine who gets there first? Of course, it will have to be the slowest person, which is Tolu. Because no matter how fast I can run, since they said we must get there together, if I run very, very fast and she's at the back, I want to wait for her to get to me. I mean, and that's exactly what happens in the chemical reaction. So the slowest reaction mechanism, which is this, the slowest elementary step, is referred to as the rate determining step for that reaction. I get it now. Note. The rate determining step, and is the step that is dependent, the step that controls the rate of the reaction. The rate determining step is the slowest elementary step. The slowest elementary step during the reaction. During the reaction mechanism. I get you now. So you can't get this thing from you can't get the reaction mechanism from the overall reaction. You can only get it from the slowest, like you can't get the rate law from the overall reaction. You can only get it from the what? From the slowest elementary step. You should write it down. Have you written it down? Now, how can we differentiate between our catalyst and our intermediary? Catalyst and our intermediary. Now, write it down. During the reaction mechanism, your catalyst and your intermediary will get cancelled out. But the difference between both of them is that the catalyst is the one that first of all gets cancelled out that first of all appears. I get me. First of all appears in your reactant, then it finally appears in the product. That shows that the catalyst was never used up. You get it? So please take note. Your catalyst first of all appears in your reactant, then now appears in your product, but it will get cancelled out. While your intermediary will first appear in your product, then in your reactant, but we also get cancelled out. So let's write it out. The catalyst in a reaction mechanism is the compound that appears in the way. I said it before, appear in the reactant, appear in the reactant, then product, but gets cancelled out. I get what I'm saying now. So before appear in the reactant, the product, but to get what? Cancelled out. While your intermediary appears, when catalyst appears as the reactant first, this one appears as the product first, then reactant appears in the product, then as the reactant, but also gets what? Cancelled out. But also get cancelled out. Now look at what we are trying to say. This is what I'm trying to say now. I'm going to demonstrate it now. I'm going to demonstrate now. Now, if I have a reaction like this, if I have a reaction like this now, if I can still turn this. If I have a reaction like this, and I've told, e.g., given the reaction mechanisms, given the reaction mechanisms, given the following reaction mechanisms now, they have told us that we have the first reaction mechanism A plus B give me C plus D. Then the second reaction mechanism the equivalent there was C plus D to give me A plus F. Now, this is what we're trying to say. Using this, they can tell you to write out. Maybe let's put 2C here. Let's put 2C here. Write out the reaction mechanism, the overall reaction, comma, the catalyst, and the intermediary. So they want us to just write out the overall reaction, catalyst, and intermediary. Another thing they can ask you for is what is the molecularity of the first step? Now, if I may ask, what will be the molecularity of this first step? Who can tell me? What will be the molecularity of this first reaction step, elementary step? This is the first elementary step, second elementary step. What will be the molecularity of this first elementary step? Someone should tell me. Okay, I've seen a question there. Now, if you are to do this now, I asked the question, I said, what will be the molecularity? I said, in this question, in this reaction step 1, what will be the molecularity of this step 1, and what is the molecularity of step 2? You guys, that means you know what the previous lecture video I dropped. That's the meaning. What will be the reaction mechanism, molecularity of the first one, and what is the molecularity of the second one? Quickly. Now, let me help you out. I said in that previous lecture that the molecularity is the number of moles of the reactant present in that reaction. Very simple. The molecularity, looking at this first one here, I have 1 mole plus 1 mole here, which is 2 at the reactant side. So my molecularity is bimolecular. The elementary step 1 is a bimolecular reaction, elementary step. Why this one is 2 plus 1, which is 3, that's 10 molecular. Nothing like try. Anything molecularity above 3 and above is 10 molecular. Now the question here is saying write out the overall reaction. How do you do it? Now in this thing, we only cancel diagonally. Only diagonally is that either like this or like this. So what am I trying to say? In this reaction now, this 2C, we cancel this 2C. I get it now. But if you check it, this 2C first of all appears in the product. If you look at this first page where we have seen it on the first elementary step, it appears in the product, then it now comes here to appear at the reactant. So based on this statement I made here, that tells us that this 2C is a what? Is an intermediary. Because your intermediary first of all appears in your product before it now appears in your reactant. Good. Then looking at this, A can also cancel A. Is diagonal. What am I trying to say when I say diagonal? Only product can cancel reactant, or reactant cancels product. Product cannot cancel product. Reactant cannot cancel reactant. So A has cancelled A. But if you look at this A now, A first of all appears in the reactant, our first one, before it appears in the product. That shows that it is a catalyst. I get it now. That shows that it is a what? Catalyst. But the fact that it first of all appeared in the reactant before we saw it in the product in the second reaction step. Good. B and B cannot cancel out. Why? Because B and B and reactant. You get it? So to write the overall reaction, our overall reaction, we just reward 2B, that is B plus B, 2B, to give you what? D plus F. So that is to give you D plus F. That's it. But in questions, normally they will write slow, fast. For you, if they want you to get the rate law, they write slow and fast. How did they expect you to get the rate law? Remember I said to get your rate law from reaction mechanisms, you made use of the slow elementary step. Looking at this, which one is the slow? This one, I mean, it means your reaction mechanism will be written from here. Your rate law will be written from this side. I get what I'm saying. Meaning it's written from that. Let's use real questions now to demonstrate this. I'll just solve one question from this aspect and we'll move away from it. Okay, now looking at this, let's write this problem down. We have the question. The following two reactions are proposed as elementary steps in the mechanism for all reactions. The following two reactions, please, we're going to do it together now, so open your mind. The following two reactions are proposed as elementary steps. Are proposed as elementary steps in the mechanism for an overall reaction. In the mechanism action. Okay. They gave us the reaction steps. They said they gave us two elementary steps. Number one, number two. NO2Cl to give NO2 gas plus Cl gas. Please follow carefully. The second one is NO2Cl plus Cl. NO2Cl plus Cl. Notice that one was not Cl2, ordinary Cl. Okay, this one too was not Cl2, ordinary Cl. To give us NO2 gas plus Cl2 gas. I see that now. So the question there that he wrote is Write the overall balance equation. Write the overall balance equation. Write the overall balance equation. Then the B part of the question, the first one, write an overall balance equation. The B part of the question, determine the molecularity of each step. Determine the molecularity of each step. Determine the molecularity of each step. Sorry, let me. If I can move this further. Okay, write the molecularity for each step. That's what it said. Now, is there a question C? Write the rate law for each step. Question C is write the rate law for each step. Please, I would advise you to use a screenshot right now so that we can move on. So write the rate law for each step. Let's be fast with that. So quickly, please, attempt the question. Attempt this question. Attempt this question, sharp. Has anybody gotten it? Nobody has gotten it. All right, sorry. So let's solve it together. Now, this one says, this is the reaction you have been given. We should write the overall balanced equation. To get that, it's just to cancel. And I told you how the cancelling works. Solution. I said that your reactant cancels product, product cancels reactant. You understand? Now, this is NO2. This is NO2. I'm actually, you came very late. And I even, well, this is NO2Cl. Is there NO2Cl in this side? No. On the first reaction, we have NO2Cl here. But in this second side, we don't have it there, so it cannot cancel out. What can cancel? This NO2, we don't have NO2 here. This Cl, but we have Cl in this place. Abi, so we can this Cl here can eliminate this Cl here. Please, if I may ask, that chlorine, the ordinary Cl, is it an intermediate or a catalyst? Is it an intermediate or a catalyst? Of course, you should know it is a what? Is it an intermediate or a catalyst? As you can see, in the first step, it appears in where? Products. Then it now came to appear in the reactant. So it is not, it is an intermediary, an intermediate. You understand? So those are the only two things that can cancel out. I told you these two can't cancel out. Product. These two can't cancel out. Reactant. So our overall reaction should be this plus this, which is 2NO, 2Cl. Are you getting me now? To give us 2NO2 plus Cl2. That's the overall reaction. Then part B, determine the molecularity of each step. Of course, the molecularity of this step here, will be what? Will be 1 unimolecular. This will be unimolecular because we only have 1 mole of reactants. For this one here will be 2 because we're having 1 plus the 1 that was on Cl, that's 2. So that one is bimolecular. So that's that for that. Then number 3, write the rate law for each step. Now, the rate law for the first step. The rate law for this step will be what? R equals to K NO2Cl. Remember when you're writing rate law, you're only using the what? Reactant side. Only reactant side. So this is the reactant. Raise to the power of how many moles were there? 1. So raise to the power of 1. So this is the rate law for the first elementary step. But the rate law for the second elementary step is R equals to K NO2Cl. I think it's as this NO2Cl. Then we also add what? Chlorine. So we now say Cl. That's the rate law of the second elementary step. Are you together now? I mean there was 2 mole here. We would have raised this one to 2. You get? So that's that for that. Now let's imagine, listen though, because I'm not going to go into it again. Let's imagine we wrote slow, fast. Are you getting me now? Slow and fast. They now ask us for the rate law of this overall reaction. Who will tell me what the answer will be? They wrote slow here and fast here. They now ask us write the rate law of the overall reaction. That's this reaction here. What will be the rate law? The rate law of the overall reaction will be this one. Why? Because that's the slow elementary step. We said we get our rate law from the slow elementary step. Please, this thing is something you guys have to get conversant with. You have to make sure you get used to it. So quickly write it down. Let's go into a very, very major aspect, which is our Arrhenius equation. Very, very important. They ask it every year. So be fast. Write down what we have there so we can move further. Are we there now? So I think I can wipe up. Okay. Okay, yes. I saw somebody just they dropped an answer. Okay. So I think I can wipe up now, right? So take a screenshot. I want to wipe it off. You are done with reaction mechanisms. So please let's listen carefully to this aspect. Arrhenius equation. Arrhenius equation. Now, Arrhenius equation is an aspect that actually enables us to study the effect of temperature the effect of temperature on the rate constant. Are you getting me now? The effect of temperature on the rate constant of a reaction. That's what Arrhenius equation enables us to do. It's just showing us how temperature affects rate constant, and of course it also brought into the relationship the activation energy of the reaction. Are you getting me now? The activation energy of the reaction, and based on this man, because it was postulated by what we call by a man called Arrhenius, and he gave us a relationship for that, the Arrhenius equation, which was k equals to a exponent. This exponent here will now be raised to the power of EA over RT. This is your Arrhenius equation, and this is using as a negative here. That's a negative there. Are you getting it now? K equals to A. This A here, let me write it properly. AE. E is standing for your exponent there. Are you getting me now? And A is just standing as a constant. How many of us are here? Okay. A is just standing for a constant. Now we know that this exponent here, if you operate with this, are you getting me now? If you operate with this, trying to remove this exponent factor here, what you'll be having will be a natural log. Are you getting me? It will be a natural log. This equation will now simplify to form in K equals to in A minus EA over R, into bracket 1 over T. That's what you have. And that's why they'll tell you that whenever you're talking about Arrhenius equation, when you plot a graph of in K, when you plot a graph of in K against 1 over T, I get me, your gradient will be this one here, this EA over R, and the intercept will be this A. Please just write it down. So that's what you have now. Now it means a graph. Now this is what we are just saying. Relate this thing to that your equation of the line y equals to c plus mx. So we are saying that thus a graph of the graph of in K against the graph of in K against 1 over T forms a straight line whose gradient as you can see, the gradient is what? Just trace it. M stands for gradient. Whose gradient is equal to minus EA all over R. R is your normal gas constant. And what? And your EA is your activation energy. Please, if you guys have questions, you can ask your question on this thing. EA is your activation energy, and R is your gas constant. I get me now. So if you give me a straight line, so your gradient is EA over R. While your intercept is going to be, look at it, this C here, your intercept is going to be in A. While the intercept is given as in A. That A is a constant, although that's our the constituent that we're dealing with, the reagent we are dealing with. Now, given that you want to check the relationship, given a situation whereby you want to check the relationship between two different reactions with different rate constants. Are you getting me now? You want to check the reaction between two different equations with different rate constants. What do we do? Now, for now, just quickly write down this. Are you getting me now? Write down this so that we can move further. Although I want to believe you guys know how we got this. Now, they can ask you actually to derive this. They can tell you to derive this. To derive this, I guess to derive this expression here, you derive it from here. And how? Look at it. Given K A E minus E A over RT, what you just do is you have to take natural log of both sides. And natural log means log E. I get me now. You have to take natural log. This is what we call natural log. What you say log. Natural log. And this natural log there actually treated as saying log E. So we are saying natural log K is equal to natural log AE minus this all over R T. You took natural log of both sides. Natural log of K, natural log of all this one. Now remember how you operate your logarithm. You know that this thing here is times in between. So if you have it in K equals to in A plus, I say that now, plus in E minus EA all over R C. So we now have in K is equal to in A plus, remember in logarithm, the number of the power here can come to the back. That's plus minus EA over R C in E. And of course, we should know that in E is as good as they are saying, in E is as good as they are saying log EE is equals to 1. Are you getting what I'm saying now? So we now have in K is equals to in A plus and minus EA over R C. And this one is out. Then in K is equals to in A. For visibility purpose, we will now write EE over R. This over T, we now separate it 1 over T. So please, this is the derivation of this expression in case you are asked. In case you are asked, because this year there is high tendency that they'll be asking you guys a lot of derivations. So you guys have to be very prepared for anything they ask. If you are done writing, just inform me. If you are done writing, just inform, please. So I think I can wipe up the board so I can show you some this thing. Okay, I can see that done. So now these are some important things now. Because you read that first formula in an expression for a Arrhenius equation, sometimes they want to check, they like to use an equation to show the relationship between two different reaction rate constants. So you will not be having two reactions. Remember our Arrhenius equation. So we say for the first one, let it be, for the first expression, let it be in K1 equals to, what is the formula? In K1 equals to what? In A minus EA over R 1 over T1. You know, for K1, the temperature will be T1, Abi. So let's now say we have another one again that is in K2, which is equals to in A, the same in A. But look at something, we're talking of for that same reaction. Are you getting me now? So for that same reaction, that this one being kept constant is A, and this is the constant, minus EA over R. Since you are looking at the temperature effect on concentration, meaning that when you change the rate constant to K2 to another one, it will be as a result of a change in temperature. That means if temperature changes to T2, our rate constant should change also, and that will be K2. Now, I want to know the relationship like this between change in temperatures. I get me on different method. What do we do? Let's imagine this equation 1 and this equation 2. We will now be subtracting K1 from K2. We will be subtracting K1 from K2. And of course, you know that if you are going to do that, if you are going to be subtracting K1 from K2, you'll be having something like this. Subtracting K1 from K2 is taken to this one from this one. What will you be having? That means you'll be saying K2 minus K1, that is in K2 minus K1. This number will be having in K2 minus in K1. Hope you are following. We are subtracting K2 from K1 in K2 minus K1 equals to, by the time we do this one, in A minus in A, I think that should give us 0 out, have you? Then we now have this one here minus what we have here. So I say this minus EA over R into bracket 1 over T2. That is this one here, minus, which will give us plus. Plus what? EA all over R into bracket 1 all over T1. That's what we should be having. Are we seeing that now? In K2 minus K1 equals to, in A we cancel out, minus EA over this one, 1 over 2, that's what we have here, minus this one here. Are we together now? It's very simple. Now, in log reading, when you have minus, what does it turn to? That division of it. So this is that say in open bracket K2 all over K1 close bracket equals to, what's common in these two? Of course, what's common is minus. You can say EAR. E over R is common, or you see minus EA over R. Any one of the two goes. Are you getting me now? So you can say minus EA over R is common. Open bracket. From this place, this one divided by EA over R will cancel, will be left with 1 over T2. Then this divided by this will be left with minus 1 over T1. Please, this is the equation you need. to solve problems. This equation is what you need to solve problems. And I'll be writing out the question now from Arrhenius equation so that we can use it to solve. Hope we are following this. Very, very important and very simple. Are you getting it now? It's just for you to subtract this one from this one. Are you getting me now? So once you know your Arrhenius equation, I'm showing you how to even derive to obtain this. So this is how you get the Arrhenius equation that relates between two different temperatures. So let's write the problem down now. Let's write the problem down. The question says the decomposition of hydrogen iodide. Problem. The decomposition of hydrogen iodide. Are you getting me now? That is, it follows this reaction 2HI gas, which will decompose to form our hydrogen gas plus iodine gas. They give you the reaction like this. Has a rate constant of this. Has a rate constant of 9.51 times 10 to the power minus 9. 9.51 times 10 to the power minus 9. I get it now. They put the unit liters per mole dot seconds. Liters per mole dot seconds. That is the unit. Liters per mole dot second. The unit of that rate constant there. At 500 Kelvin. Please, you always work with Kelvin for your temperature. I get me. And it also has a rate constant of 1.10 times 10 raised to the power of minus 5. If somebody there should be with his calculator, we're using a lot with our calculator, doing a lot with the calculator. Liters per mole per second at 600 Kelvin. Find EA. Find EA. Of course, we know that our R is a constant. R is a constant. R is giving us 8.314 joules per mole per Kelvin. The light should be going out now. So let's solve this question together. This is a question now. And this is exactly how the first question comes out for our Arrhenius equation. Exactly like this. So please, if you are writing, just stop writing and listen. If you are together, please say hi before I go on with this solution. Because I'm going to give you, immediately after this one, I'll give you one to attempt. So listen carefully. Now we have solution. Write out all your parameters first. They said the decomposition of hydrogen iodide, okay, I can see you cruising, 2HI gas to form this. Has the rate constant of this at this temperature. So you are saying the rate constant was this at this temperature. That means you can say when our K1 was equal to 9.51 times 10 to the power minus 9 liters per mole per second, our T1 was equal to what? That means our first temperature at this rate constant was, that means 500 Kelvin. Are we saying this now? 500 Kelvin. Now, when our rate constant had changed, they say, look at it here, they now said, and this at this Kelvin. So when our rate constant K2 became 1.10 times 10 to the power minus 5 liters per mole per second, our T2 now became what? 600 Kelvin. I've been given our R already as 8.314 joules per mole per Kelvin. I get it now. They are telling us to find our E. to make it like activation energy, that's EA. So making use of this formula here, we can solve the equation. We can solve that equation there. And how do we do it? Okay, how do we go about that now? How do we go about that? It's very simple. Very, very simple, and in very few steps you get the answer. It's not technical at all. How do you do it? Now, I believe you've written the question already. The question says, all you just have to do is make use of this formula here. We said the formula was in K2 over K1 is equals to minus EA over R into bracket 1 over T2 minus 1 over T1. That was exactly what we wrote as our formula. Now, let's include all those our values into it. So we'll be having in what's our K2? What do we write as our K2 here? If you check it, you can see K2. K2 was what? 1.10 times 10 to the power minus 5. 1.10 times 10 to the power minus 5 divided by K1, which is 9.51 times 10 to the power minus 9 equals to, are you seeing that now? Equals to EA is what we are looking for. EA is what we are looking for. So we say equals to EA minus EA all over. Our R was given to us as 8.314 into bracket. What was our theta, our temperature one? T2, which was 600, 1 over 600 minus 1 over, our next temperature was 1 over 500. Are you together now? So, we are making EA the subject of formula, please. Let's solve. What do we have in this place here when you press it in your calculator? What do we have? This one should press it in the calculator. This divided by this, in this divided by this. What does it give you? I'm not with the calculator here, oh. Somebody should press it. Okay, 7.053. Okay, thank you. 7.053 equals to minus EA followed by 8.314. I press this one in your calculator also. 1 over 600 minus 1 over 500. Tell me the whole value altogether. I think this value you call 7.053. Is it for in everything here or just the things here? I want to leave it for in everything there. So what will be the value of everything here? Minus 600 and 1 over 600 minus 1 over 500. What does it give us? Oh, Adama. Adama, I can see you. You're not around today. Everywhere is looking boring. I'm missing you in this place, eh? Okay. Hope you are enjoying your stay and hope you are going to come back anytime soon. All right, please, what's the value, please? When we do 1 over 600 minus 1 over 500, what do we get? What do we get? Please, someone should help me out with that now. So that gives you minus 3.33 times 10 to the power minus 4. I miss you, Jerry. So we're having 3.33. Sorry, hold on. Let me just connect this to the power source. Okay, so what do we say that value was again? Times 10 raised power minus 4. NEPA has done it again, no? They are never helping. So please, listen up. So when we now do this, we are looking for E, we say 7.053 divided as equals to now. Minus and this one will become plus. So we are having 3.33 times 10 raised power minus 4 EA all over 8.314. So by cross multiplying, we'll be having 3.33 times 10 raised power minus 4 EA equals to 7.053 times 8.314. So we're dividing both sides by 3.33 times 10 raised power minus 4. And what would that give us? This cancels this. EA will be equals to what? Someone should help me with the answer there. What will be the answer? Someone should help me with the answer. What was the answer, please? Nobody's pressing the calculator or what? Somebody should quickly press this calculator and submit answer. What is there now? Okay, I don't know. But the answer here is supposed to be giving us, our final answer is supposed to have a value of 1.76 times 10 raised to the power of 2 kilojoules per mole. Yes, so that's it. 1.76093 times 10 raised to the power of 5. Of course, we know that this is joules per mole. That's the unit for activation energy. So thank you very much, Amarati, for that value. Thank you very much, Amarati, for that value. So that's it. That's how to solve this question. It is not difficult. You just apply your formula, write out your values, insert them, and solve, and you get your answer right. So let me drop one question. Let's drop one question on this aspect also before we move to the next aspect. Let's drop one question before we move to the next aspect. Now, if we have a question like this now, they said the reaction, the rules, the reaction in reaction 2NO NOCl gas to form NO plus Cl so Cl2 gas has an EA, has an activation energy of 1.00 times 10 raised to the power of 2 kilojoules per mole. Please take note, they gave you this in what? They gave you this in kilojoules per mole. You have to convert it to joules. Yes, I just like giving you something like microfarad and micro something. Kilojoules, that's you have to times this number here by what 1000 to get it in joules per mole. Okay. And a rate constant and a rate constant of 0.286 liters per mole per second at 500 Kelvin. At 500 Kelvin, full stop. What is the rate constant at 490 Kelvin? What is the rate constant at 490 Kelvin? Question mark. Now that's the question. That's the question. Let's apply our knowledge into this to get the answer. I'll be giving you guys exactly 1 minute. 1 minute to solve this question. Or 2 minutes. 2 minutes. I'll give you 2 minutes to solve the question and get your answer. Quickly. I'm waiting for you guys. Be fast, drop your answer, and let's move on. Nobody has gotten the answer. Nobody has gotten the answer. I'm waiting. No. Okay, somebody got minus 0.699. Okay. Okay, I need another answer from somebody. Who else is attempting it? 0.699. Who else was attempting it? Nobody? I'll wait for another person. Okay, let's do it together. Let's do it together. Okay. Now, I think I can wipe off this side of the board. I can wipe off this side of the board. Okay, you made a mistake. Yeah, try it again. Try it again. Have you corrected it? Have you corrected it? Okay, 1.754 joules per mole. Okay, let's confirm now. Let's check because the answer is not here. So we'll be solving it together. You understand? Make sure you are on your calculator there so that I can help you with it. So they said a reaction D has an EA and electron and activation energy of this. So let's write it down. EA is equals to, am I writing far away from the normal place? I don't think you can see that side. I believe you have the question, Abi. So we're saying EA is equals to, based on what you had in that question, we said EA was equals to 1.00 times 10 raised to the power of 2 kilojoules per mole, of which this is equivalent to 1 times 10 raised to the power of 5 joules per mole. That is, by the time you times it by 1,000 to convert it to joules per mole, that's what you have. Then he said that the rate constant of what? Of this. So that's our K1. That the rate constant K1 of 0.26, 286. And what was the temperature at that time? At 500 Kelvin. 500 Kelvin. They also said, they now said, what is the rate constant? And they also find K2 at 490 Kelvin. That means when the T2 is 490 Kelvin. We know that our R is a normal constant 8.314 and 8.314 joules per mole per Kelvin. So we have all these things now. It's just left for us to substitute. You can easily substitute all these values in our formula. So we know our formula is in K2 over K1 equals to minus EA over R, open bracket, 1 over T2 minus 1 over T1. So that is in, what's our K2? That's what we're looking for. Our K1 has been given to us at 0.26. I think I should be able to bring this thing closer now, since they have taken the light so we can see it properly. Be able to have a better view. Okay, that's 1 over K2 over 1 over K1. K1 is 0.286, which is equals to minus EA, that's minus 1 times 10 raised to power 5, divided by our R, which is 8.314. Are we together? Open bracket, we have 1 all over. Theta and temperature 2 is 490, while temperature 1 is 500. Good. So we'll be having is as good as we're having in K2, sorry, let me write it properly. In K2 all over 0.286 equals to, when we solve everything that is here, what do we have, Amarachi? Please press in your calculator. When you solve everything here, what do you have? Just press that division stuff in the natural display, this over this, open big bracket, 1 over this minus 1 over this. What does it give you? Now, listen, let me tell you something. Somebody, I'm about to say you did K1 over K2. If you did K1 over K2, and here you did T1 minus T2, your answer will still be the same. The answer will still be the same. If you did, okay, thank you, 0.4898. 0.4898. Yes. Anytime if this formula still works, even if what you did was in K1 over K2. But if you did K1 over K2, in the temperature here, you must do T1 minus T2. That's 1 over T1 minus 1 over T2. That's it. Are you getting me now? It is not a contradictory formula, so you don't even need to be scared. You get it. If you did K1 over K2, you get, and you did T1 over T2 here, 1 over T1 minus 1 over T2 here, the answer will still be correct. But we are doing K2 minus K1, you must do, and that's your 1 over T2 minus 1 over T1 here. Okay, so what do we do now? We have to carry, because we're looking for K2, we have to carry this lane to this other place. I get it now. We have to carry this lane to this other place. So what does it give us? We are having K2 all over 0.286 equals to, please press shift lane. Press shift lane 0.489. Shift lane 0.4898. Shift lane or second function lane 0.4898. What does it give you? What does it give you? When you press shift lane 0.4898, what does it give you? Some of you are just coming. Taiwo, you just connected. Christabel, we have gone far. Although I'm going to save this lecture so that you can watch it over and over again. I know that some of your network was disturbing and stuff like that. But please, what does this give you? When you press shift lane 0, because we're looking for K2, you're carrying the natural log to the other side here to go with this 0.4898. I know the light is actually making that place blur. The light is making that place blur. Let me see if I can use my shadow to make it clear. Okay, 1.632. So by the time we cross multiply, finding our K2 will now be equals to, what will it now give us? Your network is bad. You should go to where there is network. Go under a tree. The network is always good in those kind of places. So if you look at it, that value, I'm using my shadow to make it clear. you can see is what? Is everything. Okay, so please, when we cross multiply, what does it give us? 0.286 times 1.632. What will be the value? What will be the value? Quickly, please. Sharp. Okay, the answer was what? 0.467. 0.467. And our then K is measured in what? Our rate constant is a constant. So we'll be having this. Let me see what you wrote. It's going to, the unit is liters per mole dot second. Or you say molarity per second. So that's it. Please write it down or you take a screenshot. I want to go to the final aspect of the calculation of this topic before we now use the remaining time to solve questions. Before we see if we can touch another aspect. Now, these aspects, I've already given you the formulas, its integrity laws, their half-lives and stuff like that, but we have to solve questions. So I wanted to solve like 10 questions from this chemical kinetics. I get me like 10 questions or 12 questions right now. Then if you want more questions, you can see me. I'm a bag of plenty questions. I have it in pack. They don't like, it's not even for sale, it's for free. You see it now, I'm not selling questions, I will give you for free. Okay, so can I wipe off the board, please? Huh? Can I wipe it off? Those of you that are writing. Those of us writing, can I wipe it off? Can you see it's not difficult? Okay, quickly write. It's very, very simple, of course. I know, it's very simple. So please, you guys practice questions. You know, Arrhenius equation comes out frequently too. That comes out very frequently. OBJ theory, you see it. And they're very simple. These are bonus questions for you. Okay. Can I wipe off the board? I think I can wipe it off now, right? Okay, then no problem. Adam, I had it. I will save the lecture. I will save it. Those of you that were not able to watch some part because of your network, I will save it. Which answer? Okay, I'm actually asking you this answer is the option. There is not the question, I just got the question. You understand? There is no option, it's just a theoretical question, no option, and there is no answer in it. You get? So if the values you are calling here are the correct values, then this is the answer. This is what you're asking us now. You know, you're not sure what you're calling for us again. The K2, what happened to the K2? What happened to K2? Is it the K2 stuff? Because this is the procedure. Okay, where is the error? Where do you think there's an error? Quickly, show. Which side? Because these workings are correct. But do you feel you called it wrong something for us? Because I said, what do you have in this place? You told me this is what you have, which is 0.4898. That's what you said. Then we carried our in to the other side, shift in. Okay, so help us correct it, Namarachi, quick. Where is the error? Correct it, correct it. So this value here, is this 0.4898? Or is it a different value that is here? Is this 0.4898? EA over R, EA over R. And what's wrong with it? Where is the error now? I put the minus here. Open your solving, you put your minus for us. This minus here times 10 all over this. Please, what's the final answer when you did this properly? What did you get? Let's move forward. Where are the remaining people? Don't you guys have your calculator with you? There are 3 people right now present here. The remaining of you, don't you have calculator or what? Press it to your calculator and see what you have now. The answer to that part is this part here. It's still approximately correct now, 0.490. Oh yeah, minus 0.490. So when you carry, what did you get? Abi, you start change this to minus 0.490. So what did you now get as this? If that one is minus 0.490. So this is an adjustment being made here. So what do you get when you carry your lane of this? Let's be fast. The remaining of you that are on the video, why are you not doing anything? Use your calculator and point these values and confirm it. Ah. Zero 0.613. So cross multiply, what do we now have? I don't understand. Which one is minus 7? Somebody's writing minus 7 points, minus 0.7133. You guys specify which value are you mentioning? Is it value here or here? Wait, this white light is blocking it. Let me bring it down what I have here to this place because of this white light. In this place here, what I have in this place here is in K2 over 0.286 equals to minus 0.490. Then we now have K2 over 0.286. When we do shift lean, 0.613. So then 0.613 times 0.286 gives us what? 0.175. So we said our K2 is 0.175 when you cross multiply. And that's our unit is liters per mole dot seconds. Please take notes. Take notes. This thing here, I carried it. I carried what is here because of this light. I know that you guys can't see this light. I know the light is disturbing here, this region. So from this place here, this is the next working. I don't want to write in this ring light here. Okay, we can move on. Let's go further to solve some other questions. Have you written this down? Now looking at this question now, they gave a question. We're already solving problems from the other aspect, from the integral rate law and stuff like that. He said problem. Said in a first order decomposition reaction, the first order decomposition reaction, comma, 50% of a compound decomposes in 10.5 minutes. 50% of a compound decomposes in 50% of a compound decomposes in 10.5 minutes. In 10.5 minutes. Then I said, what is the rate constant of the reaction? That's A. What is the rate constant of the reaction? Then B, it said, how long does it take for 75% of the compounds to decompose? How long does it take for 75% of the compound to decompose? Now, whenever you see a question like this, let me skip this ring light side and come and start my solution from here. Don't write it. Whenever you see a question like this, how do you know what the question is talking about? If it is you have to use your integrated rate law or something. Anytime you see a question, the question is relating concentration with time. It's integral rate law. If you look at, we're just talking about the concentration of the compound. Look at it. We're talking about the concentration of the compound. When you say 50% of the compound, we're talking about the concentration. And we're relating it with what? Time. So that tells us that we're dealing with an integral rate law. And of course, they told us in the first order reaction. So what's the formula for the integral rate law of a first order reaction? You know that the formula for the integral rate law is this. In A equals to minus KT plus in A naught. Have you seen that now? Where in A is our final conc, A naught initial conc, and K is our rate constant and stuff like that. Now they say, what's the rate constant of the reaction? Listen up now. Do you know, if you look at this, they said in the first order reaction, decomposition reaction, the first order decomposition reaction, 50% of the compound decomposes in 10 minutes. So if that means initially what you'll be having will be 100. I mean, since 50% decomposed and they are operating the percentage, that means the initially we had 100 here. If 50% decomposes, what will be remaining? Will be what? 50. Are you getting me now? And what time did it take for that decomposition to occur? 10.5 minutes. Are you seeing that now? So you put everything, all the values the way they are here. So you say for the A part, you're having in what is remaining after decomposition, after 50% are decomposed, 50 I mean, is equals to minus K times 10.5 minutes. Remember we're working in minutes, yeah? in 100. So let's look for the K. This one comes to this side, or we can say this one comes here, this one go there. You are going to be having K times, we are going to be having 10.5 K equals to in 100 minus in 50. This aspect of the topic is very simple. You can just punch this straight into your calculator rather than continue to simplify. But if you want to simplify, this will become in 100 over 50. Because 100 minus, instead of minus, it turns into division. 100 divided by 50. You'll be having 10.5 K equals to in 2. So K is equals to in 2 over 10.5. And what does it give us? In 2, we know, if you press into your calculator, you'll be having 0.693 all over 10.5 minutes. So what's our K? What's our K? You can decide to convert this minutes here to seconds by timesing it by 60. Then that means your answer will be in liters per mole dot second. But now that we're printing minutes, you say liters per mole dot minutes. You understand? So quickly divide this. What does it give us? What does it give us when we divide, please? 0.066. Okay, thank you, Juni. So we have 0.066 liters per mole dot minutes because we operated in minutes. Sorry, who is using that name, Juni? Who is using that name, Juni? Because I am not aware of anybody behind Juni. Who uses it? Taiwo. All right. So thanks a lot. Hope you understand what we are doing, Taiwo. It's not difficult, Abi. I want you guys to attend this second part. They are saying how long. Now find the time it will take for 75% of the compound to decompose. Listen, remember this thing here is not the amount. A here is not the amount that decomposes. It's the one that is remaining. So if 75% has decomposed, how many will be remaining? That means in this A here you put 25. In this initial will be 100. Whenever they are using percentage, that means initially they were what? 100. So you guys should attempt it. Attempt it sharp. Only you, only you. Okay. Someone said I should come again. I said that, but did you understand this one we did here? Why we use 100 here? Because they were operating percentage. They said in the first order reaction, decomposition reaction, 50% of the compound decomposes in this amount of time. So they are telling us that 50% out of 100, of course, they don't need to tell you that it's 50% out of 100. 50% of that thing decomposed. So since 50% decomposed, it means that initially they were 100%. And A naught is standing for our initial count. So we're just saying initially they were 100. But since 50% has decomposed, how many will be remaining when they say 50% has been used? It will be 50 that will be left. And this place here talk about our final or the residue, the final constitution, meaning 50% was left. And they give us our time, which is 10.5 minutes. But now in this second question now, they are saying how long does it take? When they hear the word how long, does it take? What do you think they're asking for? Time. Calculate the time. They're looking for T. Remember, you have got your K already. You have got your K already, which is this, which is a constant all through. You've got your K as this already. So we can put our K here. We're looking for T. It says, how long does it take for 75% of the compound to decompose? 75% of the compound to decompose. Now, it means initially there will be 100. And if 75% decompose, how many is remaining? Because A naught is the one that is remaining. A naught will be how many? 100 minus 75, which is what? 25. Can we do it now? Is it clear now? Please answer. Tolu, I don't know if Tolu can see me, but Tolu, if you can see me, I don't know. I'd love to give you pop you, but I'd have loved to give you pop, but the problem now is, mammals cannot be given annelids drink because mammals like me cannot go too low to give anthropods like Tolu this kind of drink. Tolu, is that a valid statement? I'm always happening to my phone. Very wrong my phone. The battery is already dying small small. We are not able to solve it. 21 minutes, okay, from Cruzy. That's a Marach here. Nolly. Okay, let's check it. Let's confirm. Let's confirm. 21 minutes. So that means, and let me just wipe off here like this. Of course, we know. What did Olu say? I don't even want to know what she said. Now, look at the girl is not alright, right from time. Now, look at, because this is going to off now. This is what we're going to stop for today. This is what we're going to stop. Then I'm going to give you guys question. I'll send you guys question right now to attend. Me, Platyhelminthes, Tolu, you are not well. Anthropod like you, Sarcodina. Let me tell you something. Let me not enter you. You know, if I close my can and say I want to enter somebody, it's not always good at all. It does not end well. Because I just want to stay before I start classifying you as one of these lower organisms. Just calm. Don't start where you cannot finish. We have in what's going to be remaining after 75 as decomposed. It will remain 25. In 75 equals to minus K. We've gotten our K before, which is this. That's why I not print off. 0.066 T. We are looking for T. My phone is soon off. Let's be fast. Plus in what's our initial 100 because we're doing a percentage. It said 75 decomposed. That means it was 100 before. So what will this give us? Carry this one and carry that one there. We'll be having 0.0660 equals to in 100 minus in 25. I know this in is like logarithm. I told you, you operate with it like logarithm 0.0660 equals to in. This will become 100 over 25. So it's as good as I'm saying 0.066 T is equals to in 4. Is equals to in 4, which is like in 2 plus in 2, which will be given a 1 point something something like that. Okay, so dividing both sides by 0.066 T, what do we obtain? Sorry, that's a T by 0.066. So T will be equal to how many? What will this give us? Please, someone should punch it in the calculator. Sharp. Before this phone off. Sharp, sharp, sharp. La, 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 la. What does it give us now? Is it 21 we have like this? In 4 divided by 0.066. Does it give us 21? Okay. Who uses RAS 36, please? I don't know why people find it difficult to use name, normal name. No, they don't agree to use normal name. Children, people of nowadays. 21 minutes, please. Don't forget because our K, we solved our K in minutes. You get? All right. So this is exactly where we're going to stop. I'm going to send questions now to the group. We are going to go on WhatsApp right now. Send questions to the group, and the question I'm going to send is not a question you do and wait to submit. You submit it now. I get me. Submit it now, like before you go and sleep. You get? Because I'm just sending just 3 questions. Submit it before you sleep. That's just it, and that's all. All right. So I'm logging out now.